All right, guys. It was good to talk to you guys that were able to make it to the hangout today. So hopefully we'll be doing that um, more often. So I want to finish up with the complex number review here. I think this is a review. So if not, then it is what it is. Um, but this is where we had left off yesterday with Demov's theorem, and it's basically a way to take a complex number to a power. And remember, this works for even like technically any real number is a complex number, just with a imaginary component being zero. So it works really for anything here. And the what we want to do then is we want to look at the implications of if this is raising to a power. What about if we want the roots of the number? And so starting up here, uh, to find the nth roots, right? The nth root of z we're calling w, or a lot of times omega, which we'll get into later with like frequencies when we do Fourier transforms and everything like that. So the nth root of z is a number w such that w to the n equals z. Like just imagine like that w is 3, n is 2, and z is 9. So that just means the second root of 9 is 3, basically, but this is with complex numbers here. So we're defining each to be complex. They may or may not be, but let's assume they are for right now. And so basically W has subscripts of 1 here with the Demov's theorem, or with the polar form, and Z has subscripts of 2 with its polar form. And then just a basic substitution here, if W to the n equals Z, that's using de Demov's theorem now. So R to the n cosine n theta sub 1, right? R sub 2. And the reason this has the n and this doesn't is because it's W to the n equals Z. This is our W to the n. This equals Z. And in this equation, basically, we're just equating each part of this. So if this is true, if this is an equation, that must mean that R sub 1 to the n, this piece equals R sub 2, which means that R sub 1 is the nth root of R sub 2. And then if that's true, if we're equating those two pieces, then this cosine n theta sub 1 equals cosine theta sub 2. This I sine n theta sub 1 equals I sine theta sub 2. So we're just equating each piece of that in the equation. And bottom line, to deal with the n there, right, I put here, because sine and cosine each have a period of 2 pi, n theta sub 1 equals theta sub 2 plus 2 pi k, where k is this is just a rotation, a number of rotations to get to the same terminal point when you think about trig, getting back to the same angle. So if we want to solve then for theta sub 2, that equals basically just divide this out. You get theta sub 2 equals theta sub 1 plus 2 pi k over n. Putting all of that together, right? This is our w to the n here, or rather the roots of it. So if n is a positive root, z has n distinct roots, and they could each be found in this way. So basically, these k's, right, setting equal to however many there would be, whatever root you're going to have, you start with no rotation, just the plain old plus 2 pi, right? Then plus 1 rotation, 2 rotations, etc., and you get all 8 of the roots that come out of there, okay? As always, this is probably going to be easier when we see it in action here with an example. But thinking back to what we had here, this is just like a polar form de Moivre theorem, complex numbers, but it's n of them, right? N roots. And each root has the same modulus, which is right here. That's the distance, that's the length of it, right? And what you can say is then, since they all have the same modulus, they all lie basically on a perfect circle, equidistant from the origin there. And just to show you how to use this, I typed out an example here of how to use this. And we're finding, just for the examples, the sixth roots of -8. So technically not a complex number, but it could be -8 plus 0i, and it's considered a complex number. So we're just keeping it simple here at the moment with finding roots of -8 and the sixth roots of them. There will be 6 of them, okay? So what I'm doing here is to put it into its polar form. The +8 here is the modulus, right? Think about drawing this on a complex plane. This is what I should have done on here. I ordered something, by the way, that I should be able to draw while I talk sometimes too. But if you drew, look over here, if I drew like a real number line, an imaginary number line, right? -8 is on the real number line to the left. There's no imaginary component at all. And so the distance, the modulus is 8. So you drop the negative, it's a distance. And the pi comes from the fact that if -8 is 8 units to the left of the origin, that's a rotation of pi radians, right? So the pi comes from the fact that this is 0, 90 degrees, pi over 2, 180 degrees to get just the plain old -8 gives you the pi radians. And so following the formula, the sixth root comes from 8 to the 1/6 power, which is just square root of 2, as it turns out. Cosine pi plus 2 pi k over 6 plus I sine 2 pi k over 6. And substitute 0, 1, 2, 3, 4, 5 to find those roots in there. And this is working them all out then. So 8 to the sixth root of 8 is the sixth roots of 8. I'm sorry, 8 to the 1/6 power, if you think about it, is the square root of 4 times the square root of 2 is 8. And so it simplifies down to just being the square root of 2. And then this is actually just working out to evaluating the cosine at each one of these angles. So this is where k equals 0. So it's pi plus 2 pi times 0 over 6. So basically it's pi plus 0 over 6 is pi over 6 for the first one. And cosine of pi over 6 is square root of 3 over 2. Sine of pi over 6 is 1/2. For the next one, it's pi plus 2 pi times 1 over 6. So basically it's pi plus 2 pi is 3 pi. 3 pi over 6 reduces to pi over 2. And again, just evaluate each one of those separately into there, okay? And so just continuing that on, this would be pi plus, the next one would be pi plus 2 pi, pi plus 2 pi times 2. So pi plus 2 pi is times 2 is pi plus 4 pi. So 5 pi over 6, et cetera, et cetera, et cetera, each evaluating each one of those. And those are the sixth roots of -8. So while -8 is not a complex number, it certainly has complex roots. Okay, this is just to show you that each of these angles here that you're using to get this divide out, they're evenly spaced. This has a modulus of square root of 2, or 8 to the 1/6 power. And so you've got pi over 6. You have 3 pi over 6, right? So you're adding 2 pi over 6 every time. 5 pi over 6, 7 pi over 6, 8 pi over 6, 11 pi over 6. And that's really the trick to getting the angles if you don't want to sit there and plug everything into the formula every time. Just figure out how it's spaced out, and you can just, there's 6 of them, so it's going to be evenly spaced with that. Okay, so that is how you find roots of a complex number or any number. And then with the last page here, I have complex exponentials. So this is basically raising e to a complex power. This relies on calculus. So I wrote out here, we just reviewed this when we did differential equations, but I wrote out here the Taylor series for e to the x. I used e to the z for our complex numbers. And then you'll see that some of them, it works out, that the powers of I are cyclical. So even powers of I are real. They're either 1 or -1. Odd powers of I are either -I or I. They're complex. And so what ends up happening here is if you raise e to the bi using that Taylor series, right, every other one is going to be a real number, and every other one is going to be a complex number here. So that's what we're showing here, right? This is one is a real number, real for this is to the 0 power, to the 2nd power, to the 4th power. Those all have no imaginary components, right? The odd powers retain their imaginary components. The signs change because I cubed is -1. I to the 5th is positive I again. But even powers maintain their their real component only, and then odd powers have an imaginary component. So if you separate them out, right? So this is 0 power, 2nd power, 4th power, 6th power, odd powers over here. Factor out the I, and it just works out perfectly that what you have left after you've factored out the I here is the Taylor series for cosine and the Taylor series for sine. So Euler's formula says, this is Euler's formula, if you take e to the bi, just using this Taylor series, this is cosine b plus I sine b for that number. And b again is this is just b times I being a complex number. And then if you want to have just purely imaginary number, if you want a complex number, you have a plus bi. Well, you can separate, using the properties of exponents here, you can separate out the real part for that. And then the last thing that I had down here at the bottom is this is directly related to everyone's, well, mine at least, favorite equation, that e to the I pi plus 1 equals 0 that I put down here, because if all you have to do is, the reason that works is just trigonometry there, because the cosine of pi is -1 and the sine of pi is 0, right? So e to the I pi equals -1, and you have, again, the 5 most useful, and I said famous here, numbers in math, 0 and 1, of course, all you need for binary, right? We know e and I and pi. It's great. So that's the review of complex numbers. Now, a lot of the things that we're going to be doing with matrices, especially when we do the application Fourier transform, our matrices will be filled with complex numbers, but in the form here of a complex exponential, right? Because if this is a polar form, you can condense the polar form into a complex exponential form, essentially, is where we're going to be going with this. So a lot of our matrices will be filled with these complex exponentials that represent complex numbers, okay? So I think now, Chris, now you're going to do 4 and 5 on the handout. So give that a shot today. And as always, email me with questions. We'll talk about if we need to do or ready to do another hangout soon. Okay?